sklearn, linear model, ElasticNet. Description. ElasticNet is a linear regression model that combines the L1 and L2 penalties to regularize the model coefficients. This means that it can both shrink the coefficients of less important features towards zero and set the coefficients of unimportant features exactly to zero. It is a good choice when you have a large number of features and want to select a subset of features that are most important for predicting the target variable. Inputs: X a 2D array of shape n samples. N features representing the independent features. Y a 1D array of shape n samples, representing the dependent target variable. Outputs: Core a 1D array of shape n features, representing the coefficients of the linear model. Intercept a float representing the intercept of the linear model. Steps: The ElasticNet model is trained using the training data X, Y. The model uses a combination of L1 and L2 penalties to regularize the model coefficients. The L1 penalty shrinks the coefficients towards zero, while the L2 penalty prevents the coefficients from becoming too large. The model then predicts the target variable for new data using the learned coefficients and intercept. Metrics: Mean squared error MSE measures the average squared difference between the predicted values and the actual values. Mean absolute error MA measures the average absolute difference between the predicted values and the actual values. R squared R2 represents the proportion of variance in the dependent variable that is explained by the independent variable. Root mean squared error RMSE the square root of the MSE. Visualization plots: Scatter plot of the predicted values versus the actual values to assess the model's accuracy. Residual plot to check for heteroscedasticity and other patterns in the residuals. Fine-tune parameters. Alpha the strength of the L1 penalty. Increasing alpha will lead to more features being set to zero. L1 ratio the ratio between the L1 and L2 penalties. A value of 0 corresponds to pure L2 regularization ridge, while a value of 1 corresponds to pure L1 regularization lasso. Fit intercept whether to fit the intercept of the linear model. Normalize whether to normalize the input features. Uncertainty methods. Bootstrap resampling to estimate the uncertainty in the model coefficients. Bayesian methods to obtain a posterior distribution over the model coefficients. Challenges and fixes. Challenge 1: Overfitting to the training data. Sample use case that resulted in challenge 1: A high degree of correlation between features, or a small sample size relative to the number of features. Fixes to challenge 1: Increase the regularization parameter alpha. Increase the L1 ratio. Use cross-validation to select the optimal hyperparameters. Challenge 2: High computational complexity for large datasets. Sample use case that resulted in challenge 2: Large number of features or a large number of samples. Fixes to challenge 2: Use a stochastic gradient descent (SGD) solver. Use a sparse matrix representation for the data. Consider using a different model that is more scalable, such as a decision tree or random forest.